Okay, we start the third session, which in my opinion is the most interesting one. We already discussed in the first session about the information and the geometry we mean. And in the second session, we focused on the concept of connection. And by connection, we wanted two tangent bundles to connect to each other. In this session, we would conclude our concept of connection and we'll see why information geometry out of all geometries possible on the distribution of on the space of distribution makes the most sense because of the dual structure it has. It makes the uh, geometry dually flat. We would go through all the concepts to understand what we mean by this. Okay. So we start with a quick recap from the concept of connection. Consider we are at point P on the manifold, which is represented by theta as the parameter of your probability distribution. And then we are going to see what happens to the tangent bundle attached to point P when we move P by very small distance toward partial of I. The connection gives us this distance. So if we start by partial j, and if we end up with partial j at point P plus some perturbation, the connection gives us this purple one, which can be viewed as the distance or the adjustment that we need to make in order to get the same vector in point P plus delta which is a small perturbation. So in order for us to have a connection or define a connection, we need to have access to the n to the power of 3, where n is the number of parameters we have to represent our distribution to define the connection. So there are also other ways to talk about connection. We can come up with these n to the power of 3 numbers as well, which is uh, when you connect uh, partial j with respect to vector I, and then look at the inner product between that vector, which is the purple vector here, and the partial k, what's the number? And if you have the n to the power of 3 number of parameters, you can define your connection. And there is this relationship between these n to the power of 3 numbers and the followings. And by this is the Einstein way of writing these indices. So we only look at the matching indices and we sum over them. So this is nothing but this. Okay, so we have the metric which shows the angle at each point, and we have a connection which connects each tangent bundle to another. What's the relation between these two? If you remember last time, each metric would define a natural connection, but we're going to see if we come up with n to the power of 3 random numbers, is there a reverse connection between the connection map, affine connection map, and the metric itself? So just as another recap, if we look at the Riemannian metric, which is defined by G sub ij, which is the inner product between two vectors, we could define angles which extend the shortest path, because now with the concept of angle, we can get the concept of metric on the whole Riemannian geometry. Also, the connection, as we saw earlier, can extend the parallel or straightness of the line. If you remember, we are interested in those curves like gamma and vector fields x, that when we look at the connection of gamma dot and x, it would be always zero for all t in this 0 t to 1. So it's like a parallel transport of x with respect to the geodesic with respect to the curve gamma here. So we already extend the two way of thinking about geometry. One is the considering line as shortest path, and another is considering lines in Euclidean geometry as a straightest possible way of getting one to the other. We already defined some other metrics with having the metric, the Riemannian metric G, and the affine connection. We could define the Lie bracket between two vectors, which uh, the intuition behind it is to look at the local geometry of your space. So if I go first into direction x, then y, or if I go to the direction y, then x, what's the difference? That would be Lie bracket. Then you can define torsion tensor, which is practically intuitively the same as above, with taking these three derivatives. I know the notation might look very overwhelming, but just we need the intuition behind it. So we're taking a look at this space, and we want to see how curved or torsion the space is. We just take as many derivatives as we can. And then we define Riemannian curvature, which is exactly if you have a vector space Z, what's the difference between if you move Z with respect to Y, then X, if you move Z with respect to X, then Y, and so this is the vector we have. What happens to it if we first go with X, then Y, or if we go with X, then X, or if we go with the Lie bracket of the two vectors. So in this way, we are talking about the local geometry, which we called the curvature. Okay. Now we get to the part where, so until now, we have everything built on Riemannian geometry, and now we're going to move toward the information geometry, or the geometry that makes the information geometry very special. First of all is the connections that makes everything flat. So assume the n to the power of 3 numbers we already computed for a connection to be all zero. So what does it mean if we take a look at the definition? So it means if we move from P to any other point Q with the direction of partial I, then the vector partial J would make no difference because this is T I J K. Because all of these are zero, so it practically move the partial J parallel with no adjustments. So you don't need any adjustment. That's where we have flat connection. So when we have a flat connection, it is dependent on the coordinate system. Because if you take the derivative with respect to another coordinate system, then these numbers might not be zero. So in that sense, we call the coordinate system, which makes the connection flat, to be the affine coordinate system. What's so special about affine coordinate system is that if we take a look at the geodesics, so if we take a look at these two geodesics, which are those curves that are auto-parallel to themselves, if we take a look at this would mean, because now all of these are zero, this would mean that is 1. Essentially, it means that the geodesic is simply a line. So if you start from the point P and you want to get the point Q, what's the least curved path between the two? Because you have the affine coordinate system, this would mean to have a line between them. So you don't need anything else. You don't need to consider the curve between the two. Remember, if, for example, we are on the torus, because torus has curve with respect to the natural connection, then the shortest path or the least curved path between these 2 points is not simply the line between them. But the cool thing about affine connection and affine coordinate system is that it would make the geodesics look like lines, and you can parameterize them by lines. Okay. Now, so we are interested to the flat affine connections. So later in this session, we are going to see if there exists one affine connection which is flat, and what are the according affine coordinate system for that. But before going there, I want to introduce you to one of the most important concepts in information geometry. We would later see a lot of relationship between these affine connections and divergences and the whole concept of information. So we can define alpha from -1 to +1. We can define as many connection as you want, which I show with this. And they're defined, so the only thing I need to define is n to the power of 3 numbers. So I take the partial derivatives of the log of likelihood of the probability system you have, and then I have just this alpha parameter here, and everything as stated here. Okay. So if we take a look, for example, at the one, the connection, natural connection of one, what would it be? It would be, if I take with respect to both, for example, you can consider I and J as the mean of your parameter and your variance of your parameter, the log of this, the log likelihood. And then because I wanted to put alpha equals 1, then this whole thing is 0. And then all I have to add is this. Theta. Okay. So this is so overwhelming. Let me first compute this affine connection for the exponential family. For example, consider the exponential family uh, as follows. So for at each point x, the probability respected to x is given by this formula. So what's the relationship between this and the normal distribution? So if I put theta would be mean and the variance, this would be equal. So this thing is nothing but this. So there is no connection between psi of theta. It only depends on the sigma. And of course, you can write this whole thing as your parameter system. So you can separate mu and you can separate sigma squared and write the whole thing as this. So already we know Poisson distribution, normal distribution, and a lot of distributions we see are in the exponential family. So what follows, I want to show you that in exponential family, we have an affine coordinate system. Okay. Consider the exponential family is given by this. Now I want to compute this n to the power of 3 parameters. Okay. First of all, I need to take the log of p, which would be uh, log of p. And then I need to take derivative, of course, minus this. Then, if you remember the definition I had, I first take the derivative with respect to theta I, and then I would take the derivative of the log of likelihood with respect to j, and then I would multiply it with taking derivative with respect to k. So if you take derivative with respect to theta I, then all you have is fi of x minus this. And then if you take the derivative with respect to the other parameter, because this thing doesn't have any dependencies on theta j, this is what you end up with. So if I compute the n to the power of 3 connection coordinates, I end up with this thing, which is essentially this. This is a constant. It does not depend on your expectation value. So you have to take this. Here we have x log of p, x, and theta. But the expectation is nothing but an integral or summation. So I can rearrange this and write this as, but this thing is a constant. Remember, P is a distribution. So if you take the integral of that, it would be 1 always. So this thing is always constant. And so there you have it. So we have 0 for any parameter. So the theta I are affine coordinate system. And hence, we call this exponential coordinate system. And hence, if you want to find the geodesics that this connection induce on our geometry, you only need to look at the lines when they are expressed as the linear combination of theta i's. Okay. Just to have some computation as well, I would also like to show you what these theta i's are. For example, case of in the case of normal distribution. So if we want to calculate this, these are nothing but mu to the 2 sigma squared. This is theta 1. And theta 2 is 1 to the 2 sigma squared. So whereas you could parameterize the normal distribution with mu and sigma squared, if you parameterize it with respect to these two, then this parameterization would mean that every point you have on the line between two different distribution would correspond to a geodesic. If you remember from the first session, we wanted to calculate the geodesic between two normal distribution. And as you saw, we had something like this. If we wanted to find the geodesic, which has the least amount of information loss, it would give us this thing. And if you remember from session 1, this was nothing but the curve that makes this reparameterization like a line. So if I look at the same geodesic from the perspective of our new system, mu to the 2 sigma squared and 1 over 2 sigma squared. This would look like something like this line. So in order to have an optimization of finding the best maximum likelihood estimator, already we have something to offer. Instead of optimizing over your parameter set, you should go with this parameters. Why? Because the geometry they induce or the geodesics they induce is just simple lines. They call this uh, the natural parameterization of exponential family. And we call the connection, which we showed by connection sup 1, they call this exponential or exp geodesic. Now, let me compute. So this is one extreme. We computed the connection of alpha equals 1. And now we can compute the connection of alpha equals -1. So first, your distribution. Consider this mixture family distribution. This is interesting. Why we have the distribution which equals some constant and some parameterization or some summation over different distribution. So for example, if you have mixture of Gaussians or you have mixture of Poissons or you have mixture of any distribution, so I have one normal distribution, one Poisson. I can call this with, I can show this as a mixture model. The PIs don't need to be the same. Now, uh, I want to show you that if I parameterize, so what are the parameters here? Not theta, they are eta I. If I if I parameterize this mixture family with eta, now let's compute the connection coordinate system. What I end up with is first, if I take with respect to I would get only Fi. And of course, because I had a log, I would have the same log in the denominator. And then if I take with respect to j, all I have is this. Now, if you go up and put alpha equals -1 in the definition of alpha connection, the formula would look like this. Now, all I need is to calculate the both. So this is this. And if you want to calculate this, it would be this times fj to the same distribution. And this is the magic where these two cancel each other out. And hence we have another flat geodesic. So if I parameterize my mixture family, remember in the exponential family, the parameterization was not natural as mu and sigma squared as here. But here the parameterization is very straightforward. You have different distributions. You want you want to consider all distribution over the mixture of these distribution. The very straightforward coordinate system you would go with is just going with the summation with different parameters. And we already showed that this thing in the information geometry has zero curvature. So in order to go from point P in this representation to another point Q, only thing which is natural if you consider the straight line, because the geometry induced is not curved with considering this coordinate system, that thing would be the geodesic. Okay. So we already have two way of constructing flat connections. Any question for these mixture family and exponential family? Let me take a look at the chat. Okay. Everyone can hear me as well, yes? Okay. So we started with the distribution of, with the manifold of all distribution. We had the metric, which was the Fisher information metric on this manifold. And then we found two connections. One is the alpha equals 1 with coordinate system I, which is exponential family. And another is the other we found, which I show with that J, which is mixture family. Are these three concepts living in isolated islands, or they are somehow connected? Okay. If you remember from last session, we already talked about the dual concept of two connections. So I have this metric, and then I come up with some connection, some random connection. Is there a relationship between that connection and the Riemannian metric? If you remember from last session, this was the relationship. So the intuition behind it is that, okay, the first connection is gonna glue in some way the tangent vector to another point, and the dual is gonna do it with another way of gluing. All we need to be preserved is that the inner product in the first would equal the inner product in the second point we end up with. So that's the whole relationship between the Riemannian metric and the connection. So I can go and write about the write this mathematically. So what this means is that, consider this simply as this. If I take the derivative of what's this, it's the definition of your Riemannian metric. If I take the derivative with respect to k of the inner product, it would be the same as if I take the derivative. This is I, this is k, this is j. So this is nothing but this definition, 1 of n to the power of 3 parameter of your connection. And what you do is that to have a dual connection, you put this to be equal. So this thing we assumed, which is smooth, this thing is also smooth with respect to each point. So we end up with n to the power of 3 numbers, which is smooth with respect to changing the point p. So if you give me a connection and a Riemannian metric, I can come up with a dual connection. And this thing is preserved. Okay. Now let's take a look at the alpha connection we defined here. I think I can use this. Yes. So this is the way we defined it. If we sum the alpha connection with minus alpha connection, if you go ahead and do it, I think, did it here. Okay. So it would give you, if I calculate Tij k of alpha and ijk of minus alpha, it would give me 2 plus, just to make sure I did everything correctly. Yes, exactly. Just there's no 2 here because of the 1/2. Okay. And we want to say that this equals, if I take derivative of k with respect to j. Yes. Now, I think I did the calculation here, but it's not that hard if you go ahead. So just to give you the high picture, this thing here is gonna be you should consider the inner product as the Euclidean inner product plus some surplus. So this thing, it would be this, and this thing is this. I don't want to go into the details. It would be so much indices, but you can verify that the alpha connections are dual with respect to each other. In the particular case, we had one which was theta I, the flat coordinate system, and the dual of this is nothing but -1 with another coordinate system eta j. So now we can go ahead and talk about the information geometry. How? We started with some connection, which would mean the geodesics to be flat, to be just lines. And then, given the Riemannian metric, we could build another connection, which was again, we found a flat coordinate system, exponential family coordinate system, and mixture model coordinate system. So with this thing in mind, we are already talking about special geometry on the space of all distributions. Okay, we will see the applications of this structure, but before going further, uh, I just wanted to mention again with duality, what we mean is that if I go with respect to some curve gamma from point P to Q, if I take a look at the inner product, which is uh, the relationship between the Riemannian metric and the connections, if I take a look at that, that thing would be constant as I move along the curve. And also, we found out that the both connections give rise to flat structures. And flat structures means that if I take any other curve, the points or the vectors attached to the points would behave the same. So no matter what curve I take, the inner product would be the same. That's where the connection, Riemannian geometry, and the Riemannian metric are all playing together. Okay. So if the connection is flat, then the affine connection between the two does not depend on the curve. So you can go with whatever curve you want as long as you have flatness because there's no curvature. Okay. Before I continue, I need to go and talk about another duality we have, which is in convex optimization, Legendre transform. And I wanna talk to you about why we call this dual and that thing duality as well. So there should be a connection between the two. And also, if you remember from first session, we talked a lot about chaos divergence, but we didn't talk about that in principled way of thinking. So here, the whole information thing came out of chaos divergence, which showed the uh, entropy in its formula. But what's the relationship between Riemannian metric and chaos divergence and all other divergences? Okay. Before I continue, if anyone has any question about connection, dual connection, and its relationship with the Riemannian metric, and also flat connections and flat coordinate systems. Okay, let's dive into the concept of divergence. Divergence between two distribution P and Q is not a distance, is just a heuristic for the distance. So we want the divergence between two distribution to be always positive and to be always zero only if the two distributions are zero. This is what we want from divergence. And also, we want it to be strictly convex in this diagonal. With we would talk about this later here. Okay. Now, we want to connect divergence. So we have two distributions. We have some uh, heuristic about the distance between these two. But when we talk about divergence, for example, when I say divergence, just recall chaos divergence, there is no indication of the underlying geometry. But we already saw that the distance between two distributions where relied on the geometry a lot. So where's the geometry in divergence here? Okay. In order to do that, we need to first uh, connect divergence to the Riemannian metric. Okay. I thought a lot about this. Uh, let's forget about all these calculations I did here for a moment. Consider, I want to estimate P plus some perturbation and P. Okay, I want to calculate this. If you use Taylor expansion, what this means is that this is plus some first order derivative, second, and third derivative of D. And then we have epsilon to the power of 4, something, forget about it for now. So this is where I want to bring in the geometry. So in order to connect divergence to Riemannian geometry, I say the second order derivative, this thing should look like the Riemannian geometry. And the third order one, this thing should look like the connection. So given a divergence, I want to give you a Riemannian metric and also connection. In order to do that, I need to give you, in the first case, n to the power of 2 numbers. And for the second case, I need to give you n to the power of 3 number of parameters. So how's that? Okay. Remember that vector fields in our Riemannian geometry were nothing but the push we needed from going one distribution to another closed distribution. So if I lived on this Riemannian geometry, P, then XP, which was the attached vector field of X, is nothing but the push. If I go ahead and do this, this would give me another distribution with another thing. So one way to calculate these is to take derivatives. And derivatives, remember that we showed the vector fields on the whole Riemannian geometry we had with partial derivatives. And now it makes sense. How? Okay. I define, first of all, let me take a look at the chat. Heard. Okay. 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 So define the divergence between two. So now I want to define vector fields on the divergence. So if I take the derivative with respect to the first distribution and the second, remember, this is nothing but a vector field. This is nothing but a vector field. I define it to be the derivative of the resulting divergence between the two. So I first calculate the divergence and then take the derivative with respect to the second. parameter and then with respect to the first. And then I look at the limit of this thing when P prime goes to P. So I just take a look at the diagonal operator of the divergence. In that way, so I would define this again, like above. I take a look at D of P and P prime, each represented by two coordinate system theta and theta prime. I then take with derivative with respect to theta and then theta j. And then the resulting, I take a look at this. It's nothing but calculating the exact Taylor expansion coordinates if I talk about divergence in this way. So now, if you take a look at this thing, the divergence between the divergence operator we defined here, when I have only one vector field, it would be zero. Why? Because this is nothing but taking I divergence of P and P prime, and then look at the limit of P prime, distribution P prime going to P. But this thing, because of the first uh, sorry, the first relationship I had for the divergence to be zero only on the diagonal, this would be zero. So the first coordinate of Taylor expansion is zero. Now, if you take a look at the second order Taylor expansion entry, it would be something like this. Now, I define this to be the Riemannian metric. Remember, this thing was this. What's the inner product between two basis vectors? Here, I defined it to be the minus of the divergence of the two basis vector fields. Now, it looks very natural to define the connection in the same way. Why? Because connection, remember, in order for you to have the definition of connection, only you need n to the power of 3 numbers. So I need to find this. And in order to do that, I just define it to be this. So given a divergence, if I look at the Taylor expansion, I'll get the second order estimation would give me Riemannian metric, and the third order would give me the connection. So given a divergence, I already defined this and this. And again, with the two, remember we can find the dual connection. If you go ahead and calculate the dual connection, you'll see that the dual of P and Q, if I look at the dual in the sense of divergence, if I define it to be P, so I just swap P and Q. If I look at the dual of divergence and define it like this, it would give you the same metric. So if I start with D star instead of D, it would give me the same, which equals to G of D. And if I look at theta D star, it would be nothing but the connection of the dual connection of the first connection I found here. And hence, because we had this nice symmetric relationship between dual and the connection and the Riemannian metric, it's easy to see that the dual of this is nothing but this. So given divergence, we defined a connection and a Riemannian metric and its dual. Okay, this is the calculation in case any of you is interested. So again, this is I remember that I did the calculation above. So if you take a look at this, it would give you exactly, if you look at the definition of the connection parameter, it would be some inner product with three number of vectors, which is this, and this is also this. And if you use, so I can bring the derivative outside, this is something you can do. Derivative operator is linear. And if you bring I outside in both cases, it would be this, but this is nothing but the definition of the Riemannian metric sub Kj. So we have the duality of the connections. Now, out of all divergences, uh, if any of you has taken any information theory class, you are familiar with the concept of F divergence or Bergman divergences. They use the following divergence. So for a convex function, which is 0 at point 1 and is strictly convex at point 1, you can define the divergence between P and Q with respect to that function to be this thing. Okay, let's do some calculation just to get handy with the F divergence. For example, F is convex and we are calculating a weighted average of these creatures with respect to P. We know, so this is nothing but expected of P of F Q P. We know by Jensen inequality that this thing is greater than or equal because of convexity of F than this Q over P. And this is nothing but F of expected Q and because Q was a distribution, this is 1. So we have that df is always greater than or equal f of 1, which is, we already assumed it to be 0. So we have positivity of the divergence. The other thing is the strictly convexity at the diagonal, which we already have this here. And also, if we want, consider df of P and Q to be 0. Then this is nothing but f of 1. Then we need the equality on the Jensen equality, which then translate to all this weighted average individuals to be 0, in our case, to be equal. And that means P equals Q on all for almost everywhere or on all x's. So the second, third, and all three conditions for a divergence is satisfied. So we have defined a class of divergences here. Now, there are a lot of literature about divergences. Only those we are interested in is the duality and how the duality works here. So we already defined d star of f to be equal to d of q and f. So it's like integral of px f pq instead of qp. This thing also q. Then if you define the dual of f as this, which any one of you who has taken convex optimization knows that f star is nothing but the uh, Legendre transform of f, would give you the same dual divergence. So right now we have some sense why we call the duality of connections duality. Because connections can come from a divergence, and divergence, we have defined a duality for divergence, which comes from the duality over functions. And that thing would create another connection, and these two would be dual. So the duality in all senses, functions, divergence, and connections, Riemannian geometry, have all came to the same point, that we know duality in everything to be the same. Okay. Also, uh, the same as the alpha connections, there is this formula that if you put the function f in your f divergence to be equal minus log when alpha equals -1 to equal x times logarithm of x when alpha is 1 and use this, then df of alpha, which I show with abuse of notation as d alpha of f, or d alpha, if I take a look at g of d, and if I take a look at the connection induced by this divergence, this is nothing but alpha connection we had. So we started from divergence, we started from functions, and we ended up with the same connections. And again, if you take a look at this and this, they are related with respect to the dual formula of functions. Okay. And also we, if you want to get the KL divergence, the only thing you need to do is to consider f to be f equals alpha minus 1. So the KL divergence We have it in this formula as well as the F divergence when F equals minus logarithm of U. Okay. Also, some other application-based of properties of KL divergence is as follows, that the KL divergence of the product of distributions equal the summation of the each part. Okay, we'll get to this in the application sessions, which is the latter two sessions. So right now, we have came up with a way that by defining divergence, we have the geometry. And no matter the divergence we start from, which was essentially uh, all these class of F divergences, if we look at the Taylor expansion of them, the second of them, GD, would equal the Fisher information matrix, which is constant. So no matter divergence you come from, the induced geometry or the induced Riemannian metric would be the same. But this is not the case for the connection. The affine connection uh, changes as you change your divergence. So we had a number of connections, especially exponential connection and mixture family connection. We saw already that KL divergence, if we take a look at this, it would be df of minus 1. If you remember, we showed through calculations. Actually, we didn't show, we just used the knowledge. If we put alpha equals that, then the induced affine connection would be the same as alpha connection. This is this. And if you remember from the first half of this session, for this connection, the affine coordinate system was nothing but the eta i's, which were the mixture of models. So if we go linearly, just linear in the sense linear of mixture models, of the first component of KL divergence, we are walking through the geodesic. So it shouldn't make any change to the KL divergence of any distribution P and Q and any geodesic of P here and the corresponding Q. Also, we knew that the KL divergence and F1, alpha equals 1, were dual. So if you change Q with respect to the second geodesic, it would also does not change. So we found somehow this parallel dual families of distributions. Okay. Now, in the remaining of this session, we would try to do the magic of connecting all these things together. Okay. We already defined Riemannian geometry on the space of all distributions to be dually flat. Why? we could find a coordinate system, which is the exponential family coordinate system, or one in another notation we used, that the geodesics were lines. So there was no curvature if we use this parameterization of the whole space. Then we found another parameter, another way of parameterizing the same space, which was through mixture of models. That again, if we look through the lens of that parameter, then the geodesics are nothing but lines. So we call this structure, so when we have a Riemannian metric, a flat coordinate system, and then the dual of that coordinate system has also another flat coordinate system to be dually flat structure. So we already saw that information geometry, which is nothing but the geometry induced by Fisher information metrics on the space of all distributions, to be dually flat. Okay. Then, if you remember from the definition of Riemannian metric, we have this. And if we go to the dual representation, of course, these would change. So now what is this? This is taking the derivative with respect to n eta j. This was taking derivative with respect to theta I. Consider this two way of parameterization. For example, this is theta and mu squared, sigma squared for the usual normal distribution. Then this is eta 1, this is eta 2, and theta considered to be minus mu 2 sigma squared to be theta 1, and 1 over 2 sigma squared to be theta 2. As you can see, the two kind of parameters, why we care about this. First, because they make, each of them make the geodesics very natural as lines, but it would make the metric and everything to be recalculated for each coordinate system. So if you go ahead and calculate this and reparameterize, so you can calculate it in the first parameterization. If you go into the second parameterization, it would give you the inverse of Fisher information metric. So again, this is another way of understanding the duality. So in the dual, the Riemannian metric induced by the dual coordinate system is the inverse of the first Riemannian metric we had. Okay. Now here is where the things get really interesting. So consider I want to represent the second coordinate system, eta, with respect to the first coordinate system, theta. One way to do so is to find a function, psi, that when I take the gradient with respect to theta, it would create us the second parameters. Okay? So we want to find psi. Why? Because we want to translate theta to eta. Okay. If you take any ordinary differential equation system, you know that in order for this to have an answer, because you have some function psi that given theta gives you some float number. If you take the gradient with respect to that, it would create you another vector. And now we want this system of ordinary differential equations to have answer. For that, we need psi to have this property. If I take derivative with respect to I, then j, it would be equal to taking derivative with respect to parameter j, then I. Okay? If psi has this, then we're good. We can find this psi that translate theta to eta via this relationship. But wait a minute. If we take, so this thing is nothing but eta j, but if we take uh, the derivative with respect to theta I of eta j, if you remember from the calculations above, it is nothing but the Riemannian metric. So how we can find this psi function? We solve another second order derivative equations. How at each point we want the second derivative of psi to be equal to the Riemannian Fisher information metric. Okay. And also it would make psi, because this thing, if you remember, the inner product was uh, positive definite. So it would make psi and also phi, which is the other way around. If I want to translate etas to theta, it would make both to be positive definite, and it would make psi and phi to be convex. Okay. Now uh, is the most interesting part, where if I have the function psi, I can create the function phi. How? Define phi of any eta, which is phi of q of eta. Remember, eta was a parameterization of distribution. Define it to be the Legendre transform of psi, which is the inner product of theta and minus psi. Okay. This is not magic, of course, because if you, for example, find the supremum of this, you need to take derivative with respect to theta. If you take that, the first derivative, it would create eta q, and the second one is nothing but this. And we defined psi to have this relationship. And this relationship occurs where we have the maximum of the function. So this is not magic. This is the way we define the function psi and phi. It would make them the Legendre transform of each other. Okay. Now we have two coordinate system and two functions that translate each coordinate system to another. And we already know how to find them. Okay. What's the relationship? So we have the psi. Now we can find the connection and everything. Take a look at the second derivative of psi. You have the Riemannian metric. Take a look at the third order. You'll get the connection. Okay. And remember, the first connections with respect to each of them were equal to zero because eta and theta were both the flat coordinate systems. Okay. Now I want to find a way to go around this circle. So we had a divergence. We could define the metric and connection. Now I want to make a process that from a Riemannian metric and a connection, I can create a divergence. This is the way of defining the canonical divergence that helps you to go all the way around. So you have the Riemannian metric. Take a look at the second derivative. Create psi. Take the Legendre transform. Create phi. And then define d equal this. In this way, so we started from G, we could create phi and psi. Then with this, we created this divergence. And then with this, we already saw we could create some other Riemannian metric and some other connection, affine connection. And the cool thing here, so we already had also theta and this. The cool thing that happens here is that through calculations, you can see that the first Riemannian metric equals the second. The affine connection you started with is the affine connection you end with. So we close the loop. Whether you come from a divergence, which is the whole concept of information transmitting from two distribution, you can create a Riemannian geometry. From the Riemannian geometry, you can create the divergence also. So the two concepts of the Riemannian geometry and the divergence, we found the connection, and also we found the duality. We knew duality in the Legendre transform. We called the function phi the dual of psi here in any optimization course. We now saw that the induced affine connection of phi would give you the dual of the induced affine connection of psi. So this is the whole puzzle that we have. Also, we have another very important thing here, that the induced E-flat geodesics are exponential family, and the induced M-flat of the dual of the first is the mixture model geodesic. And both of them are flat. Okay. With this being said, we have the final, yes, actually, I can go over the last two in the next session, but we have the very last thing to say. So Pythagorean theorem also holds. How? If you define the divergence between two distributions with respect to these two functions, so these functions are not special. The special thing is the two dually flat coordinate system that helps us to define the divergence like this. Again, it's very simple because of the definition of psi and phi, which was the supremum over a set. And for you to see that this D here would satisfy all the conditions of the divergence, you could see through this that if you want to calculate, to have the triangle uh, condition where you have for any metric D in a metric space, you take a look at this, and this should be bigger than this. Now, this does not hold for any divergence in the general case, but this way of thinking about divergence would makes us able to talk about what's the difference between these two, and is nothing but the canonical two flat coordinate system, the dot product of them. This is the usual Euclidean dot product of the two parameter sets. With this in mind, you can have Pythagorean theorem as well. How? If you have a triangle like this thing is 90-degree in what sense? In the sense of Riemannian geometry. So if you take a look at this thing is 0 at point P, at point Q. If you take a look at the divergence between these two and between these two, it would be exactly the same as the divergence between these two plus some regulator, which equals to 0 when we have the 90-degree. So we could come up with a triangle relationship if we go all the way around from the dually flat structure. The emphasis here is to remember that all these things that helped us create this divergence is the existence of the dual flat coordinate system. If we have that, we can create all the divergence and triangle property as well. Okay. With that in mind, I want to conclude this session. So we started from Riemannian metric and connection. We ended up with a divergence. We started with a divergence and ended up with a Riemannian geometry. So now we have the full mathematical tools we need in order to go for the applications. Just to give you an overview of the application section. So we start from a problem which is defined, for example, find the minimum of the divergence between two distributions, the true distribution and the distribution parameterized distribution you want to find. We already know the geometry and the only geometry because we go in both directions governing the two distributions. And then we can walk through the geodesics, which are happen to be linear geodesics. Just to have it here. Yes, I don't think I have enough time to go over the exponential family and the resulting psi and phi and the canonical coordinate system and the canonical divergence. But if you may guess, the canonical divergence would be nothing but the KL divergence for the Riemannian geometry we have here. Okay, next session, we will go through the applications of what we built, the mathematic we built, the dually flat structure we built on the information geometry, And we will take a look at its application in machine learning and in the last session in financial uh, market and how we can model that. Okay, if you guys have any questions, you're more than welcome to say now.